And I want to thank you guys for coming out and joining us, maybe rejoining us as the case may be. Of course, we're out here to talk about AI for system programmers, and I think this is a optimal time to be talking about that because one of the tools that we have, Image Focus, and its functionality called release analysis, employs an AI that's generally available throughout the integrity controls environment and can clearly help you get ready for your migration, excuse me, to 3.2. But as we get started here, I want to take an opportunity just to do something that might level set us all to understand more clearly where we're coming from when we talk about AI. So this is a very high level picture here, and the question is, what is artificial intelligence? Well, essentially, artificial intelligence is an attempt on our part to create a machine, in our case, a smart program, that can solve a complex problem and provide an answer that would be viewed as having done something smart. That is, that it is giving us an opportunity to review a finding that it makes, and we look at that finding and we say, oh, that's a smart thing to do. I understand where that came from and what it's attempting to tell me. Of course, in order to create such a machine, such a smart program, we need to have some data to train it with because it just doesn't materialize on its own. And there are a number of different methods that can be used for that training. It could be supervised, that is, somebody's watching it very closely and implementing all the rules and other constructs that are necessary for it to perform its task. Or it could be unsupervised, which essentially means it's training itself. It's training itself to understand huge, large amounts of data in ways that sometimes are just not clear to us as human beings. Of course, on the other side, that is, when the findings are made available, it's critically important for us to measure its performance. And performance typically in AIs is based on the percentage of how often it was proven smart. That is, how much we can depend on it, how credible we believe its findings are. And of course, in the case of ZOS and system programmers, that performance has to be 100% or at least approach 100%. So in summary here, what we're trying to do is solve a complex problem. And those problems could be, what is the current state of the running system? What is its configuration? How is it changing over time? Or it could be, let's set up a clean room in order to be able to uh, proceed with a secure boot. These are complex problems and they require substantial amount of data and training, and the findings would often be viewed as doing something smart, but they have to approach or maybe achieve 100% in terms of their accuracy. Now, there are lots of different kinds of AIs that are out there. There's probably a new one that comes along every day. But the four major categories of AI are shown here in this slide. Rules and large language models essentially have as their goal to make a prediction. In those cases where we have rule-based models, they predict an outcome based on the establishment of rules that are generally viewed to be true. Large language models, on the other hand, have as their prediction capability to predict the next word, the next pixel, the next sound or note. Quite different one from the other and require completely different methods of training. In both cases, the training is supervised. That is, that some data scientist is in essence managing the creation of the model in order to assure that its performance will meet some criteria. In the case of rule-based models, they turned out to be fact-based retrievers. In the case of large language models, they tend to be based on labeled data sets, that is, large data sets that have been groomed, cleaned up for them to process through whatever process they are being trained with in order to come up with valid predictions. The performance of rule-based models is generally viewed to be 100%. That is, that the data scientist can know what the rules are specifically, know how those rules are supposed to function, and know the data that it's being trained against, and can deduce, and often using eyeballs and perhaps other sophisticated mathematical methods, to determine that the answers are in fact correct and reliable. In the case of large language models, it's sometimes hard for the data scientist to actually determine through visualization or mathematics whether the answer in fact is true. And the difference between achieving 100% and 98%, that 2% difference, is often referred to as a hallucination. That is, the model just simply produced or predicted an answer that's just not right. But it's very difficult to figure out why that happens. There are often ways of adjusting the model. The data scientists will use biases, as they're often called, to manage the mathematics behind the predictions, but still, hallucinations can occur. On the other side, general AI, or Gen AI as it's called, and RAG, which is retrieval augmented generation, don't make predictions, they generate something new. They generate something based on a prompt that is given to it that says, make me a fuzzy dog with green eyes. Okay, well, there's no fuzzy dogs with green eyes for us to learn about in the real world, so they just generate one. And so these answers then become, in some ways, comical, hilarious. In some ways, they turn out to be valid because they're predicting protein structures and other kinds of things like that. The learning that these guys go through, that is Gen AI and RAG, is unsupervised. That is, the models learn essentially on their own. The data sets that they use are unlabeled. That is, the data is all scrambled up, and the models themselves have mathematics that allow them to figure all that out. And it could be that in some cases, when Gen AI is not capable of approaching 100%, that it is augmented with old-fashioned AI, that is rule-based AI, in order to perform ancillary functions that give it an opportunity to to improve its performance score, in this case, in this example, up to 98%. So there are a whole bunch of different kinds here. The kind that we are talking about when we talk about AI for systems programmers is rule-based AI, fact-based retrievers that either are at 100% or can achieve 100% because the data scientists who are programming them can easily change the rules and the retrieval prompts that are necessary in order for them to perform their job. There's one other thing which is beginning to gain prominence as well, and that's angenic AI. And this is a form of AI well beyond that which is clearly available for the general public today, that operates essentially on its own, at times in the wild, if you would, on a network, performing tasks that are hopefully have controls that allow them to be turned on and off as necessary. But they are AIs that call other AIs to perform other AI type tasks for them, far beyond the sophistication that we are talking about when we're talking about AI for system programmers. So, what are we actually talking about? Well, here's an overview of Image Focus and its AI functionality, how this thing actually works. And quite often, people refer to this as old-fashioned AI. This is the way it has been for years and years. You probably have written an AI of some kind or another. You probably have trained a program to recognize data and perform certain tasks on it, and may not have thought of it as an AI at that point in time. But as time went on, the terminology caught up with you. And now that program that you might consider to be highly sophisticated is actually a form of AI called old-fashioned AI. Now, we have been doing this for a long, long time. And so the techniques for actually training the model are well known to us. We use things like experience, our own experience. We use the experience of our customers because there are often conversations that go on between us and our customers as to the veracity of our findings. And we're open to understanding your point of view on that and provide you even with certain methods that allow you to perform bias tweaking of the model itself. Things like providing a test parm lib that says, don't test the running system, test this new system, this 3.2 system. Here's my changes, here's my work, here's my effort. Test this for me and let me know whether this will work in my environment. Or providing you with filter rules that allow you to change the outcome in a way that best fits the needs of your organization in understanding, again, the veracity of your ZOS environment. Of course, the data scientists are always watchful for PTFs and for changes in formal documentation. And as those arise, whether it's for ParmLib, or JES, VTAM, TCP/IP, or CICS, many others like Pageant, for example, they make updates. They retrain the model in order to be able to deal with those updates and changes. And those are made available to our users and those that are in the middle of proof of concepts so that they can evaluate them, test them, give us feedback on them, and ultimately refine them to the point where we achieve that 100% veracity in the outcome. Now, the outcome of the model are findings, and as we produce them, they are errors, warnings, and notices, or simply informational. They are, in fact, deterministic. That is, that we know in advance what the finding will be under certain circumstances. That's part of the training. The results of the findings are recorded in an inspection trace, and that trace can be quite large, in some cases between 18 to 20,000 records in size. But the facts are that what you would find in there are fact-based information about the configuration of the targeted ZOS system and transparency about the finding. You can find the answer in those 18,000 records somewhere. But performing data analysis on that data set, that prediction data set, can be complex. So there's another side to our AI that allows for us to present you today with a different view of it, not a view from SDSF or 3.4, but a full view from the command line that allows you to immediately gain insight as to what the findings are and how they might impact your environment. And we'll spend a lot of time dealing with that demonstration later on. Of course, what we're specifically talking about here is IPLCheck AI. And to be clear, IPLCheck AI is image focus, but it is running exclusively under the IBM Health Checker for ZOS. That close association with the Health Checker not only allows it to identify potential problems in the configuration of your ZOS environment, specifically augmented in this case to determine whether or not there are any dynamic changes that may have taken place, that is, changes between the hardened configuration in ParmLib and that configuration that's actually being used by the system at any point in time. And additionally, that association allows it to detect the exceptions that are being reported by the health checker and combine all that information into a single set of findings that can be made available to you so that you see not only what image focus is able to report, but also what the health checker is reporting at the same particular point in time. So it's really important to understand that all of that is a lot of data. I mean, I know you've heard many times about the stories about big data and how it can overwhelm you. That inspection trace that is produced by IPLCheck is large, and being able to explore it in a systematic way is critical to the configuration insights and other compliance concerns that you might have that are not just obvious by reporting errors, warnings, notices, or exceptions. So there are a number of different ways that you can approach the exploration of the trace itself. You could just simply depend on SDSF, the upper left-hand corner here of this particular slide. Or you could work with ICECheck, the one that's in the middle that I'm about to demonstrate. Or if a more sophisticated approach, a more graphical approach is desired, then ICEDirect and our web portal could help you there. So I'm going to stop sharing this here and go to a 3270 session because that's where we're going to spend the majority of our time now. So here we go. So it's a basic 3270 session, and I'm going to go to SDSF, and we're going to type in CK. This will give me a list of all of the health checks that are currently active. And I'm going to do a find on NEZ. And I don't get anything because there are no NewEra checks active at this point in time. So I'm going to go back. I'm going to go to ST, and I'm actually going to start IPLCheck. Oops. Guess I better start IPLCheck. That looks better. Now, IPLCheck is a relatively simple installation. Once it's installed, the installation libraries can be shared across multiple images within the same sysplex, or maybe not in the same sysplex, but sharing DASD with where the original installation has taken place. Once it's started on any individual system, it registers itself with the IBM Health Checker for ZOS, and from that point forward is executed on whatever schedule you have set up for its execution within the constructs of the Health Checker configuration. So now I'm going to go back to CK, and we're going to do a find on NEZ. And so here are all the NewEra health checks that are all either running or finished at this point in time and have done their thing. From IPLCheck's perspective, there are two checks that come standard with it. One is called the Dynamic Change Inspector. That's that reconciliation, if you would, of what did you specify in ParmLab and what are we actually using. We can take a look at that. And it's pretty straightforward in the sense that, excuse me, it's telling us, and get down here, that the areas that it looks for dynamic changes in APF list, BPX list, BPX PARM, linked list, LPA, and system symbols, all of them are the same. That is, there's no changes from ParmLab, but there is a difference in the LPA list. And so this probably for some of you will be enough information. That will be all you need to know, but it's not going to tell you what those differences are at this point in time. Those differences are in that log, in that trace of the events that it went through to make that determination. On the other hand, the second component of IPLCheck is the OPSIS inspector. And here it is right here, and we can take a look at that. And I'm on a development system, so there's limited security, and so you can see that one of the findings that is being made has to do with rack route failures, protection inadequate on data sets, and in my case, this just goes on and on. Things like bad load libraries not found on the volume that they're specified on. That's not a good thing. Naming them incorrectly. There's a lot of security related stuff inside of the trace because the model has been trained not only on the HarmLab data sets and their constructs and the path and IEA and SIM and all that, but it's also been trained on the security needs that are associated or surround the ZOS environment itself. So it, in some ways, serves two functions. One, to make sure that the IPL path is viable from a construction perspective, but also viable from a security perspective, which is critically important because bad guys will do bad things. And being able to find those data sets that don't belong or have been added or have made changes becomes a critical part of what the model is essentially trying to do. So that's it. That's what you get with IPLCheck, except with IPLCheck AI, recently rebranded and available with our delivery of 3.2, you could actually do this. You could go to the command line and type TSO, dollar, command line interface, comma, CK. Now, this is one of several different AIs that we have, as I'll talk to you about later. On the 23rd of this month, we're going to introduce you to ValBoot AI, which is an AI that's been trained by rules to help you to set up the key rings, the certificates, the profiles, the permits, and the testing environment that will allow you to quickly establish a clean room for managing the requirements for a secure boot. So we'll talk about that later this month. So I'll go ahead and hit enter. This works from any command line. So go out and figure out what the trace log is. Here it is up here, IFO, BAT, IPLCheck. This is system name and this log. We could put the cursor under that and we could actually see the log, okay? And we could page down to the bottom of it and get this out of the way. We can see that that guy is 18,101 records long to get to the bottom of the report. So there is just a ton of information in here, not just errors, warnings, and notices, but compliance reports and other kind of information about the configuration itself and the relative parts of the configuration that don't necessarily fit into trying to answer questions about is it good, is it bad, that require you to spend time evaluating what has been discovered here. Now that's essentially, excuse me, that's essentially what this is all about. Giving you the opportunity to discover through your own analysis, your own visualization, what it is about this that is interesting to you from a compliance perspective, from a general understanding, exploration of the data. Typical kind of review that anyone would do for any AI and the output that it produces. Now let's start at the top here so that you can sort of understand what's on this screen, because like the trace itself, this is an overwhelming amount of data and will take some time and some experience and some exploration before you clearly understand it. When the health checker last ran, so it ran today at 8:20, so it ran when I said start. The age of the checks is 0 at this point in time, so there isn't anything to worry about. That's brand new. The IFO that actually ran, that is the level of image focus that we're running at, is 18J50. This is a critical element of information to understand, because remember, the data scientists are constantly upgrading and retraining the model itself based on experience and new PTFs and new documentation, your experience, etc. So knowing this can help us to understand if debate rage about, no, that's not right, you missed this, that didn't happen, why aren't you inspecting this? It could be because you might be back leveled and need to get up to speed. We release these updates frequently, and so staying current is critically important. Of course, we looked at the trace itself. We also do additional inspections with our supplemental inspectors, an extra license that covers off things like cert auth, resolver, profile, data, pageant, etc., etc. And if you have this, you also get a global summary of the findings that are associated with those particular inspectors. And so you can see from this global finding that there is something awry, errors in the FTP client server at this point in time, and would draw your attention to that to make appropriate corrective actions or take appropriate corrective actions. Of course, you can search the trace if you want to. Now, here's a search facility that can get you in touch with data sets, members, user IDs. What has the users been doing? What users actually are impacting this particular system? Well, Larry's impacting it. He did it 4 times, and these are the lines in the log these are the numbers in the log where he actually made his impact. Here's the line numbers. Here's when he did it. Here's the member he did it to. Everything you need to know. Who's doing it? Why are they doing it? When did they do it? How did they do it? Etc. You can see the findings. You can see the findings from the last execution of the health checker. So there's been no change. You can see the history. You can see here, we ran on the 7th, we ran on the 6th, we said there was no change. But when we ran on the 5th, we had 122 warnings, and then we jumped to 144. Not good. Something's gone on. We need to go find out what that's all about. And we went from 0 dynamic changes in LPA to 6. And so there's some activity that's going on that we probably should be curious about that's taking place between the 5th of October and the 6th of October. When we go back, we can see additional information about the IPL last. The last IPL was on September the 15th. At this time, it's 22 days old, and it was for V2R5. This is the unit address. This is the load parm. I can see specifically what those load parm values were. Whoops, sorry. Whether we're on the running system, not on the running system, what is it that we're doing? PF3. What does the load member look like? Trying to answer all the questions that you might normally have about what is this? I have this report, what is it? if you had just one system, this wouldn't be so daunting. But we have some users that have hundreds of LPARs that are being inspected by IPLCheck. And keeping track in your own mind as to which ones are which and what's going on can become daunting. And not to put a damper on it, but just knowing that it inspected clean is probably not all that you need to know, specifically right before you quiesce a system and plan to upgrade it before you bring it online again. You need to know about those dynamic changes. You need to know that there are no changes in symbols or APF or BPX or mounts, some LPA changes, 6 in this case. What are they? Well, here they are. So through some process, one or the other, who knows, 5 modules have been deleted and 1 module has been added. And you might ask the question, to what or where or how? Well, the page down a little bit, we might get the answer or at least some clues as to where those changes might have come from. So, or where we might have to add them or delete them or whatever. So we're not only telling you what has changed. Remember, we only said, yes, there's something that changed. Now we're telling you specifically what has changed and where you're likely going to need to go. The name of the member, the data set it was found in, the volume that it's on, and the user who last touched it. So these are critical pieces of information to help you quickly diagnose and update your ZOS environment. Another aspect of this component of IPLCheck AI is your ability to be able to build a baseline of the configuration itself to determine any base configuration changes that might be occurring to it. And that baseline looks like this. It's big as well, no question about it. Has containers that contain various elements of the configuration itself. And so here's one of the containers. This one is called IPL path, and it contains all of the elements that are in that IPL path that should be of interest to you in trying to figure out if any changes are taking place to the base configuration. You notice the container begins and it ends, but all the information that's within the container has been tokenized, so that should a change occur to this baseline itself, then that would mean that somebody's manipulated it. And so if it has been manipulated at the time we attempt to do a comparison, we would actually report that and say it as possible that your baseline has been manipulated and you should either find out why or at least consider renewing it. What do changes look like? Here's one change. And you can see it's telling us, okay, so we had one delete. We're talking about IEA sim. We had one delete of a symbol definition. We had 3 adds of symbol definitions. We can't specifically point you to a spot where it was deleted, that is, the current member is new, but we can point out those that are new records in that member that are new. Here's one. Here's another one. So these are the 3. These are the ones that have been added, and that other guy had been deleted. This simply goes on, just exploring what is in the trace itself, answering questions about what's in the trace. There are some discovery prompts that are critically important. One might be to know what Unix system services look like. So these prompts will go against the trace and extract the information that's necessary in order to produce a report. So here's a report. These all have common headers. tell us where they came from. These are all of the Unix files that have been referenced in this particular configuration. Here's where they came from, and here's the members that are associated with Unix system services that are in this particular inspection trace. Of course, at any point in time, if you chose to, you could say, that's important, and I better send that off to John. So let's send him IPL path by member by date. Here's the report, TF3. Here's the message that you might send to John. Here's the report name. Here's his email address, and we can send the mail now. So you don't have to go figure out how to copy it, put it in a data set, attach it to an email, and send it. This will do all of that dynamically for you. There are other functions here. You can copy and print it if you want to. That's also possible. These are very powerful functions, so there are also guardrails that can be turned on using a facility class profile of our making. The guardrails are currently on. They can be turned off. Now they're off. Now they're back on. Only admins have access to this panel for actually updating what's going on here. There's automation associated with this, levels of monitoring that can go on, different reports that can be sent, dashboard report, a findings report, a health check exception report. This one's kind of interesting because it provides a more in-depth look at the check exceptions that are being reported by the IBM Health Checker for ZOS. All of these checks have high-level exceptions, and knowing that could be important, knowing which ones are not scheduled to be run again. This one's age is 15, hasn't been run in 15 days. We can put the cursor under any of these to reveal a history of the check itself, if we choose to do that. And this one has no specific history of itself. We can look at all the checks that are associated with a specific owner, like RACF, for example. These are all the RACF checks. You can see this one, GRS RNL. Another dynamic change element that we would report on if, in fact, it was active. And then we can, in turn, look at all of the checks themselves. What did it say? So you don't have to go to the health checker. You don't have to go to SDSF. You might not even have SDSF to get the answer as to which checks are being reported as exceptions. See that first, and then answer the question, what other checks does that particular owner have that may or may not have exceptions? And here's more for RACF. Finally, there are different methods of delivery of information from IPLCheck AI and its analysis of the trace. You can interface with ServiceNow if you choose to do it. You can also interface with FTP, and we support both regular FTP and secure FTP. It's really straightforward. Just simply decide what you want to send, the full log, the dash report, the findings report, the health check report, or alternatively, an alert, and simply start the transfer. You'll get all the messages that are associated with the send itself, and when it's done, you'll get a response from the system that says the transfer was successful of 18,119 records. In some cases, like in the case of Alt, because I don't have it actually set up, it'll try to send that as well. So you can send in a series, all, none, whatever you choose, and it will come back and it'll tell you, in this case, there was an error because we couldn't find a specific alt data set, and that we have a file transfer error. So you can set this up from an automated perspective. Let me get back here by simply checking this. And either on this schedule that's set for the delivery of email ServiceNow notifications or FTP, that will go automatically. But you need to test it, and that's what I was just showing you. You can, if you choose to, simply turn off all of our scheduling and gently rely on that FTP to be called directly, excuse me, by the IBM Health Checker or ZOS. Okay. All right. Excuse me. Let me go back here just a moment. So I hope it's clear from the demonstration that there is a lot of information in the trace that needs to be examined more closely than just simply a cursory, oh, we passed all of the inspection points, there's no issue. Well, that may be true, and for some of you, that may be all you want. But for those of you that are interested in a deeper understanding of the configuration, because this may be a system that's new to you, you may have been called in to help to assist in understanding what's going on, or there are simply compliance issues that you have to respond to that require reports to be created and sent to specific targets, either FTP targets, ServiceNow targets, or simply email targets. As I mentioned, what's up next is going to occur on October 23rd at 8 Pacific, and it's called ValBoot AI. And essentially what it is a smart program, an AI, that understands the rules associated with building the software requirements that are necessary to establish a clean room for the management of your ZOS configuration. The key rings, the certificates, the permits, the profiles, and not only that, but also an opportunity to test all of those to make sure that they will function or continue to remain functional over time so that the clean room can remain as you expect it. So that's our story for today, AI for system programmers, just in time to help you get ready for 3.2. I hope you enjoyed this and found it interesting.